Hey, look at that.
I'm working on it, Mr.
It's
Sims.
an actual instrument, though. I'm impressed. It's not spoons.
I can really do this. I'm gonna...
Hey, it's like an actual song coming out of there, too.
So you theater people, what song is that from? Even though I'm doing it quite poorly, right?
I don't know what that is.
You don't really know?
No, what is it?
Is the theme from Fiddler on the Roof.
Oh, I see. I think
There was
seen
a
that once.
fiddler on the roof.
He was, and if he was a rich man, I don't know. There's
If I were a rich man.
Yeah. That wasn't too bad. You know, that was no cowbell, but
It was not a cowbell, but it wasn't bad.
yeah, it wasn't too bad. I'm impressed. I'm impressed. I really am.
Yes, indeed. Well, you know,
All right, ladies and gentlemen.
better than I, you know, actually, maybe the violin is my instrument.
Perhaps.
It needs a little bit of work.
Yeah,
I
I'll
think.
keep exploring that one. All right, so podcast 4.5 is the last one for chapter 4. We're going to be looking at reaction stoichiometry.
So, hey guys, on this one, the trick is, I don't have any sets of rules for you. I don't have. It's just we're going to work some problems.
You just do it. Yep.
We're just going to work problem 1, 2, 3, 4, maybe 5 and 6, whatever it is, and we're going to solve a bunch of problems. I will say one thing here that you should write down somewhere on your paper. The key equation. The key equation is M times V equals moles.
Yep.
And we did this some time ago, but if you don't do this, you don't know nothing. So you must find everything and convert it to moles.
Always.
Always to moles.
Convert to moles. No matter
Moles
what it is.
or nothing. It
Convert
must
to
be in
moles.
moles. Or actually millimoles is even better. So we will do that as well.
Yep. Here we go.
Okay, all right.
Most of the things we'll have are in milliliters.
Milliliters, millimoles. Like Millie is good. Like Millie, like Aunt Millie. She is the lady from your past.
I had a cat named Millie.
Did you? I have
Mildred.
no cat named Millie.
Mildred.
It's just
So
Mildred.
he's a fiddler on the roof. Now he's acquired a quasi-Russian accent.
Russian? Maybe so.
Is that what it is?
I don't know what
I don't
it
know
is.
what it is either.
All right, I'll try to be clear when I talk. Okay, now,
Okay, here we go.
frankly, these screens I have on here are going to do me no good at all because I need lots of space.
We need
to
lots of
write.
space.
So I'm going to go right to the back. By the way, do you understand, Mr. Sams, what the background is?
I see a bunch of dead trees.
Dead trees is exactly what it is because they were killed by...
Pine bark beetle? Oh,
No.
acid rain.
Acid
Sorry.
rain. These
Right.
are acid rain.
Those of you out in
dead
internet
trees.
land, a lot of our trees are leaving to the beetles. But yes, acid
Okay.
rain, that works too. Sorry.
Barium chloride. So
Absolutely.
now, it is a stoichiometry problem, so I must
Yes.
always start with a...
Balanced chemical
You must have
equation.
it balanced. If not balanced, it's bad. Okay, balance it. Okay, so we have barium chloride. So that's BaCl2. Now, in this case, I'm not going to revert to the net ionic like we did in the previous problems because you want to work with a full ionic equation. I like that way first.
Yeah.
So barium chloride reacts with...
Sodium sulfate.
So that's Na2SO4. Now, I'm going to do this pretty quickly. That's just play the charge game. You look them up if you need to.
Yep.
That's going to do a double replacement, and you're going to make barium sulfate and NaCl. Now, to balance this equation, you will simply need your problems with your sodiums. You'll need to put a 2 in front of the sodium chloride.
Looks good to me.
Now, something you also probably will need to know is which particular product is a precipitate.
Yes.
And how would you need to know that?
Nacl-noso.
Nacl-noso. And you see, we have a nacl here, so that means he is...
Definitely soluble.
So that means that, also, nacl-nosos, all
So,
sulfates are soluble.
Except for
Oh.
few, and barium is one of those
Barium,
few.
lead, and mercury.
Yeah.
And barium is an exception. So this right here is
And
the
calcium.
precipitate. And calcium, that's correct. All right, and so now I'm going to write down what I know underneath what I know. I have, of the barium chloride, I have 10 milliliters. And I have it at a 0.25 molar solution. The sodium sulfate
Also 10 milliliters.
is also 10
but
milliliters.
0.35
A
molar
little
solution.
bit more concentrated. So I'm just writing data down. All right, now this is going to introduce what I like to call an ice table. All right, so we're going to just kind of create a line under here. It's like having like a data table underneath here. Okay, and you're going to kind of see this. And I stands for initial, or the initial amount of each chemical. Now, the barium sulfate, how many initially do I have there, Mr. Sam?
0.
That's easy, and the salt is also 0.
Because we don't have any products yet.
No
we haven't
products.
mixed our
This is
reactants
before
together.
the reactants have mixed together. And so now I'm going to convert these to millimoles. So I'm going to use what equation, Mr. Sams?
Molarity times volume.
Molarity times volume. And now I'd like to work with millimoles, so I can just take 10 times 0.25. Now, you rock and roll scientists, it's very easy. The number is 2.5 millimoles. And this, of course, will be 3.5 millimoles. Now, this is actually, if you think about it, a limiting reactant problem. You must find out which one you're going to run out of first. Now, the beauty of this first problem is that the mole-to-mole ratio is 1 to 1.
Yes, very
And
nice.
so, the one I have the least amount of is the one I will run out of first.
And frankly, guys, doing limiting reactant problems this way, I think it's a lot easier than doing limiting reactant problems the other way.
So now I'm going to, which one is the limiting reactant?
Probably the one we have less of.
So that makes the barium chloride the limiting
since
reactant.
they're 1-to-1 ratios.
Now the C, by the way, stands for change. So we're going to lose some of each of the chemicals as the reaction transpires. So you're going to lose all of the limiting reactants. And how much will you have remaining?
0. It's
0.
all going away.
It's all going away. And that's not totally true. We'll explain
Well.
that. And then this, of course, is going to lose the same amount. Now, it's important to note that it's the same amount because this ratio is 1 to 1.
Right.
If it's a different ratio, we'll do an example like that. And, of course, what's left over is 1 millimole. Now, the barium sulfate will go what? What will happen? Now, again, this is a nice 1-to-1
ratio. Looks like we're going to gain 2.5.
He's going to gain the same amount of millimoles, so his total amount of... By the way, did I say this? E stands for the ending amount.
Yes.
Sometimes equilibrium, if you're doing an equilibrium problem. This is not an equilibrium problem.
Nope.
And this, of course, will do the same, but I'm going to ignore this, and you'll see why. Because it's a NaCl, it's a soluble product.
It still stays dissolved.
Now, the big question is, what are the concentration... Actually, how many grams of precipitate form?
Yeah, that's part B in your question.
Part B. And so the question I want to answer is, if this is my moles of precipitate, actually my millimoles, I then simply will do a conversion. I'm going to do it on a separate sheet here because I want to save some space on that sheet. If I have 2.5 millimoles of barium sulfate, and I will say... Now, I'm going to do something a little bit different. I'm going to say that 1 millimole of barium sulfate is equal to so many milligrams of barium sulfate. Now, this is simply the molar mass expressed in milligrams per millimole. So you just go onto the periodic table, and it's 233.3 milligrams. That is just simply barium 137 plus sulfur 32 plus oxygen 16 times 4. And the millimoles of the barium sulfate cancel, and you just multiply by 233, and you get 583.3 milligrams of barium sulfate. Now, if you need to convert to grams, you would just divide by 1,000. That'd be 0.583 grams of barium sulfate. You could set that up if you needed to, but that is essentially the answer to question B. Now, the second part, I want to go back to my previous screen.
Real quick, as a side note, guys, on your handouts, on letter C, at the end in the parentheses, it says use a BCA table. That's the same thing as an ICE table. It's just another way that I've done it before. And it's before change and after versus initial change and end. The reason I call it a BCA table is when we do get to equilibrium and we use the ICE table, I just do them so they have different names, but it's going to work the same way either way.
Well, maybe we could go with BCA. We'll go with BCA on this one, and I like that, Mr. Sims.
Okay.
We'll go that method.
We'll go BCA and then
Now,
do ICE for equilibrium?
Yeah, I think that's a good call. On the letter C, concentrations of ions present. Now, that means, now what ions are present? All right, let's think about this reaction here. I really would like to have a space here, but we have barium, we have chloride, we have sodium, and we have sulfate.
Right.
And one of the chemicals is totally used up.
Yeah, all the barium chloride gets used up.
Well, that's not exactly true, Mr.
Actually,
Sims.
all the barium
Only the
gets
barium
used up.
in the barium chloride gets used up,
Right.
because the only thing that made the precipitate in the barium chloride was the barium.
Right.
So the chloride is actually, we want to find the concentration of the chloride. Now here is the kind of critical point. I had 2.5 millimoles of chloride, and since over here none of it reacted,
Still an ion.
It's still an ion. Now, we do have a bit of an issue here, is that we do have a 2 here. It's BaCl2. So when you have BaCl2, let me do it on a blank screen here. If I have 2.5 millimoles of barium chloride, and none of the chloride got used up because it's still kind of hanging around as an ion. If you were to draw a flat beaker or whatever, you would find the chlorides hanging out, just floating around, but you'd find 2 of them for every 1 unit of barium chloride.
Right.
So actually, how many millimoles of chloride do you have?
We'll just have to multiply by 2, so we'll have 5 millimoles of barium chloride.
So the concentration of the chloride ion will be equal to 2 times 2.5 millimoles. That's the moles, and molarity, of course, is in units of moles per
liter.
And so if we knew the number of, actually, if we put milliliters on the bottom, then my millis will cancel. The total volume of the solution, now if we go back...
Total volume, we started with 10 milliliters of barium chloride, and we added 10 milliliters of sodium sulfate, so that's a total of 20 milliliters for our total volume.
So I simply will put in here, on the bottom, 20 milliliters. So it's going to be essentially 5 over 20 a fourth. Is that 0.25?
It
Mr.
is.
Sams? So that is 0.25 molar. You see? That is the molarity of the chloride. Now notice I also use these brackets, and the brackets represent concentration in units of molarity, which of course is moles per liter. But also it's in terms of millimoles, that says millimoles, per milliliter. I did it too fast on my tablet. Okay. So we did the chloride, and now we want to do the barium. Actually, we could really quickly do the barium. What is the concentration of the barium?
0.
That's Ba2 positive, and there are none of that left over because it's all used up.
It got all turned into barium sulfate.
So that leaves us with the sodium and the sulfate. Let's do the sodium because it's also part of the sodium chloride and did not react, and there's a 2 right there. So for the sodium, so the concentration of the sodium ion will be equal to there was 3.5 millimoles of that. Look at the problem there. But there's 2 of them because it was Na2SO4. That'd be times 2 again because of this 2 right here. And that'll also be over the total volume of 20 milliliters. And my millis will cancel, and my molarity comes to be 0.35 molar. Got it? And then the last one, of course, is the sulfate. Now this one's a little tricky, but not horribly. So the concentration of the sulfate, let me go back to the initial screen again. So if you find the sulfate right here, this is where this 1 comes into place.
Right. Because 2.5 of the sulfates got used up, we've got 1 left over. 1 millimole left over.
So that'll be 1 millimole. We don't have to multiply that by any number.
There's
actually
just 1
millimole
per unit.
Divided by our 20 milliliters. 1/20th is 0.05. Yeah. 0.05. I think we can keep 1 more digit. Molar there. And that is the answer.
Them are the ions.
That is the answer to the question.
Yeah. Now, one other thing, just as far as terminology goes, and our problem here says, what are the concentrations of all ions? It could have said, what are the concentrations of all species present? That's just another term that's used for things floating around in solution. You'll see that in the book and on the AP test.
This is really kind of a big accounting problem. It's kind of how I see it. You got to account for all of them and then just keep track of all your numbers.
That's why these tables are handy, the BCA tables and later the ICE tables.
Yeah. All right. So example 2 is a similar type of a problem. This one has some coefficients, and that's why we choose this one. And so here's example number 2. So I'm going to start with a nice white screen. And so we have sodium phosphate. Sodium has a charge of +1, and phosphate, hold on, let me just, is -3. So it's Na3PO4. I guess I don't need to put the parentheses there. Nope. Plus
copper 2 chloride.
CuCl2. Now that's going to double displace. Now sodium with its 1 charge and chloride with its 1 charge will make NaCl.
NaCl.
That's the NaCl. But this other one's going to be quite complex. It'll be Cu3 parentheses PO4 2.
Right. So that's copper 2 phosphate.
Copper.
Mr. Bergman, if it's copper 2 phosphate, why is there a little 3 after the copper?
Because it's the charge that matters when you say copper 2.
Thank you. Just wanted to make sure.
It's all about the charge. You see, that 3 is not now. Now we need to balance this equation. Now when you're attempting to balance, you look for the most complex compound.
Yep.
That would obviously be the complex compound. So I'm going to do my copper first, because I need 3 coppers from here.
Yep.
And I have 2 phosphates, and I put it 2 here. That gives me how many sodiums?
It's like 6 sodiums and 6 chlorines.
And I get 3 times 2 or 6 chlorines.
Perfect.
So that is the correct balanced equation. I'm going to write down what I know. I have
50 mils
This is 50 milliliters of
0.1 molar sodium phosphate.
0 molar.
And 50 milliliters of 0.1 molar copper chloride.
Is 50 milliliters of 0.10
Now,
molar.
don't be enticed by the sneakiness of that. You still have to look at the mole ratios. Do not go, oh, same volume, same concentration, must be all 1 to 1 to 1 to 1. It's not. We must look at the mole ratios. Be careful.
So B, C, A.
Before, change, and after.
Now, we're going to do M times V equals moles, so 50 times 0.1 is simply 5 millimoles. And this is also 5 millimoles. You might say, well, we have exactly the same amount of each. And that is somewhat true, but it is true. But the problem is well, what is the issue, Mr.
They react in different ratios.
Because we have a 3 here and a 2 here. Which one will you run out of first?
Let's see. We're going to use up the one with the greater coefficient first.
So the limiting reactant in this case is the second chemical, or the copper chloride. So how much of this are we going to have go away?
That's going to all go away since that's our limiting reactant.
So that'll be minus 5.0, and that A, what they stand for?
After.
After. Duh. Okay. Mr. Bergman is so used to his ICE thing.
And it's Friday afternoon to top it off.
And it's also before a holiday weekend, so we are tired.
Why are we here? Oh, wait, that's right. We have to get these done.
And I was up at 4 this morning to swim. So, yeah, one of those things. Actually, I got well, it's been a long day. Okay, so now we have to figure out how much this goes away. This is a little tricky because of this 3 to 2 ratio. Let me just set it up for you. I think it's better to understand it dimensionally.
Definitely.
So if you have 5 millimoles of the CuCl2 over 1, then what you'll do is you can say there are 3 millimoles of CuCl2 to 2 moles of Na3, that says Na3PO4. Now, Mr. Sams, where did I get that 2 and that 3?
Those are the coefficients from the balanced equation. That's our mole ratio.
And so you simply just convert from moles to moles, or millimoles to millimoles, and you get 3.33. So this will be minus 3.33. So 5 minus 1.67, did I do that right, Mr. Sams?
Yes, you did.
1.67 millimoles.
Millimoles.
Now, the sodium, we didn't say this, did we?
Let's go ahead and
the sodium chloride is a NaCl, so this is aqueous, or it is a soluble compound, NaCl, but this right here will be my precipitate.
That is.
Okay, so this starts at 0, this starts at 0, and this will be plus, now we have a 1 here, so when we compare it to a 1/3, essentially if you kind of figure this out, instead of multiplying by 2/3, you're going to multiply the 5 times 1/3. Hopefully you see that. I'm not going to work that out. That's 1.67, or a 1.67. So this is kind of our basis to solve the problem. Now we're going to try and find the grams of the precipitate. And the grams of the precipitate, of course, is the copper 2 phosphate. And we have 1.67 millimoles of copper 2 phosphate. So if I have 1.6, this is part B, 1.67 millimoles of the Cu3 PO42, I then need to calculate the molar mass of Cu3PO42. So that'll be 3 times 60.
63.5.
3.5, that's the copper right there, plus 31 times 2, that's the phosphorus. How many oxygens are there in that problem?
Total of 8.
8 times 16, that's the oxygen. That adds to a pretty hefty number, 380.5 grams per mole.
Guys, double check that and make sure Mr. Sams did it right. I'm pretty sure it's correct.
380.
That's what we're going to go with.
0.5 grams in 1 mole. That's of the copper phosphate. I won't write the copper phosphate, but you get a grand hefty total of 635, probably 3 digits, milligrams of the Cu3PO42. So that's the grams of the precipitate. Now we want to find the concentrations of all the ions, as it says, or you could say all of the species. So I will then go back to my previous screen, and let's chat about the chemicals. Let's actually start with the copper. I think that's the easiest, the copper chloride right here. Now, which one was used up, the copper or the chloride?
The copper got used up because the chloride is still dissolved.
And there are a double there. So let's do the copper chloride. So with the copper chloride, all right, the concentration, so you have copper chloride, and we had 5 millimoles. So I'm going to say the concentration of the Cl negative will be equal to 2 times 5 over our total volume. I think our total volume would be 100.
It was 100, yeah, 50 milliliters plus the 50
milliliters, that says milliliters, and that 2 times 5 is 10.1, isn't it? 0.10 molar. All right? So that's our chloride concentration. Now if we jump back to our screen again, so we've got the chloride taken care of. The copper is 0. We can maybe write that down. The concentration of the Cu2 positive is 0 molar. It's all used up. And now we, of course, have the sodium and the phosphate to deal with. Now, the sodium has a little 3 there, so let me kind of bring this screen. We have 5 millimoles of Na3PO4. So the concentration of the ion Na positive 1 will be equal to 5 millimoles times 3, due to this 3 right there, divided by 100 milli. It'd be 15, isn't it?
0.1.
Yeah. Be 0.15 molar. Now, if I want to find the concentration of the phosphate, this one's a little bit tricky because, of course, some of it was used up in the making of our precipitate. So if we jump back to that screen, the phosphate, we had 1.67 moles. So I'm looking at the A column. So that's 1.67 millimoles divided by 100. I can do this in my head. Milliliters, and that'll be 0.0167 molar.
There it is.
And that's the answer to question 2. And these just are going to only, you're going to get good at these by like doing them. Doom, until you're done doing them.
Yeah, next. Now those were both double replacement reactions,
That's
forming
correct.
precipitates.
So here's our acid-base reaction.
Acid-base
But guys,
reaction.
this is not any different. It's the same exact
same
process,
thing.
it's with a different type of reaction. It does create a couple of issues which we're going to face as we deal with this. So of course I'm going to jump to a blank screen. So we're going to react sodium hydroxide. I love this. Hydroxide, which of course is NaOH.
Roll that R.
With acetic acid, HC2H3O2. Now it's also essentially a double replacement reaction, but it makes what?
All acid-base reactions make water. The H goes with the OH to make HOH.
And then the other chemical will be sodium acetate.
Yes.
Both sodium and acetate have a charge of positive 1 and negative 1, or you know, and then they cancel. This is a balanced equation, so all of our things are 1 to 1 to 1 to 1. So what do I know about our
20 milliliters, 0.25 molar sodium hydroxide. And then it's titrated with 23.2 milliliters of acetic acid. To the phenolphthalein endpoint, what is the concentration?
Okay, this
of the
asks
acid
sort of
that
a
you wanna
different
know?
question. We're not asking for concentration of the
No.
reactants. We just want to find what is the concentration of the acetic acid. All right. So, but again, the thing I know things about is the sodium hydroxide. So I can do. This isn't a BCA table.
No,
folks.
I would just use regular old stoichiometry rules to do this. Reason being, we're not given information about both the reactants. If we had full information about both, we would probably do the BCA.
But if I have a molarity and a volume of a particular chemical, I like to just do M times V equals moles.
Perfect.
So 25 or 0.25 times 20. Is that not 5?
It is 5.
So that is 5.0 millimoles of NaOH. So actually that's of NaOH, and guess what, folks? That is like my beginning of my stoichiometry.
Yep.
Now I want to convert to the acetic acid, and so I can say 1 millimoles. This is now, these coefficients you're used to thinking of as mole to mole, but they can be millimole to millimole.
Yep. They
So
could be molecule to molecule if you
yeah,
wanted
that's
them
true.
to be.
1 millimole of NaOH is 1 millimole, if I can write today, it's light, of acetic acid, HC2H3O2. Now that's the moles of acetic acid. Turned out it was a 1-to-1 ratio. And I'm going to do it this way, I think. And so that's, of course, 5 millimoles of acetic acid.
Yep.
Now we're trying to find the molarity, and probably should have said this earlier, but molarity is moles per liter.
Or millimoles per milliliter. Hey, look, we have millimoles.
And guess what? We
have milliliters.
So to find the concentration, we simply take the 5 and we divide it by 23.2 milliliters, and we get a grand concentration of 0.22 molar. Probably I could keep one more digit. Maybe 0.215 molar is the exact answer.
Okay, that's that.
Let's look at our next one. It's another acid-base problem, but it's asking for something slightly different. All right, again, we have a balanced equation.
Actually, that's the same thing. What's the concentration of the acid?
Oh, it is, but it's got a different ratio.
Different ratio, yeah. So
that's
we're
why I
gonna
have
have to
it.
do
Okay,
different
so
things.
we've got NaOH.
Yep, NaOH and H3PO4. Oh, if you did the Pepsi project with us,
You have seen this
You
reaction.
have seen this reaction.
That makes HOH and Na3PO4.
You're very familiar with this
This reaction you are probably sick of. Balancing it, you need a 3 here and a 3 here. Now, what do I know about this?
Oh, we've got 10 milliliters of 0.5 molar sodium hydroxide.
And the phosphoric acid is?
23.2 milliliters. Hey, same volume again.
I think I did the same problem. I made these up in my brain, so it's probably demented. So M times V here, that is be 5 millimoles of NaOH. You simply are the only thing here that's going to be different, ladies and gentlemen, is instead of a 1-to-1 ratio, then I'll say 3 millimoles of NaOH is equal to 1 millimole of H3PO4. When I do the math, or Mr. Sam's on my sidebar here, it's 1.67. Probably we can call that 1.7 millimoles.
Yeah, if we're doing 2 sig
figs. So the concentration of the phosphoric acid will be 1.7 millimoles divided by 23.2 milliliters, and that's going to be a tiny number, 0.073 molar. So that's a pretty quick problem. So these acid-base ones, they usually ask for one thing instead of like 14 things like that other one. And this last acid-base problem, it asks you to find a molar mass. Now, before we figure this out, we need to kind of define molar mass. What is molar mass again?
Molar mass is grams divided by moles.
So if you know the grams and you know the moles, you take the grams and you divide by the moles.
Right. And hey, look in the problem, 0.523 grams of an unknown acid. We're just going to plug that right in.
So we already know the grams.
We already know half of the problem.
So if we knew the moles,
we just plug it in and that's it.
We plug it in and that
divide.
would be it. So we do have a reaction. Reactions.
Unknown monoprotic acid.
Mono?
Mono means one.
Mono means one,
Yes.
So it means it's got one what?
One proton
protic.
or one hydrogen ion.
So that is, we're going to just call that HA. Because, and we'll assume that A has a charge of -1. Yes. Plus, what's it reacting with?
Oh, it is reacting with sodium hydroxide.
Oh, the old sodium hydroxide. Have we seen that a couple of times today? I think believe so. That makes HOH and NaA. Now, in this particular reaction, we have a 1-to-1 to 1-to-1 ratio.
Convenient.
Is that too many ones? I don't know. Whatever. Okay. So what do we know?
We've got 0.523 grams of our acid. And that's going to go in the top of our molar mass calculation. And for the base, we've got 22.5 milliliters, and its concentration is 0.103 molar.
I see a molarity and a volume, Mr. Sanders.
I do too. I'm going to say we're going to turn that into millimoles.
So we just multiply MV. So M times V, so 0.103 times 22.5 gives me a grand...
2.32, we'll round it.
2.32 millimoles of NaOH. If I could convert that to millimoles, or actually to moles, I'm going to want to go to moles in this case. You'll see why. To moles of HA. Now I'm going to use that mole-to-mole ratio. 1 millimole of NaOH is equal to 1 millimole. Where did I get those ones again?
Those are the coefficients of the balanced equation.
Yeah, that's right here and here. And actually, on this case, guys, I'm going to go one more step, because actually now I do want to convert to moles.
Right.
I'm going to then say 1,000 millimoles is equal to 1 mole.
Yep.
And I get a number that is quite small.
0.00232.
And that is the number of moles of HA. Now, we knew we had 0.523 grams of HA, so if I take 0.532 grams of HA and divided by 0.00232 moles of HA. Grams divided by moles gives me a molar mass, and it's 225 grams per mole.
Weird.
Big. That would be a big acid.
Huge.
Well, it would be like a citrix and some of the bigger tartaric and stuff like that. It could happen. Well, guys, we have just one more problem in all of Chapter 4 left. This is another reaction stoichiometry problem. The only problem that's different here is this is a redox stoichiometry problem. This one's a bit more cumbersome because we have to spend time balancing the redox equation.
And also predicting the products.
Oh,
of the
and
redox
I make
equation.
you predict the products. I make these up.
What a doozy.
And I have to solve my own problems. KMNO4 reacts with iron FeSO4.
Iron 2 sulfate.
Is it an acidic solution?
It is. The solution is acidified.
So that means it's, so we have to think this through. Permanganate. So look on that table from last unit or whatever. If you want to, if you know what I'm talking about, I'm referring to, assuming Mr. Bergman can find it in his slideshow.
There.
Here it is. This is the reaction. Permanganate turns into manganese 2 in an acidic solution. All right. So I'm going to just balance this equation. MnO4 negative is going to turn into
Mn plus 2.
Mn2 positive. I think I underlined the wrong one on the chart, but this is the correct answer. Oh well. This will be, then I got to balance the O's first. The Mn's are balanced. So I'll say 4 waters.
Mr. Bergman, do you want to talk at all why you left out potassium?
Because I shouldn't have. Okay. My mistake. Thank you, Mr. Sams. And so I need to put potassium on this side, don't I? K positive. And I'm going to then need 8 hydrogens on this side. And I need to balance the charges. Now I've got 8. This has no charge. There's no charge there. And this is going to be 3, 8, 5. There'd be 5 electrons, right?
Yep.
Okay. Now I've got the FeSO4, and it needs to go up.
Right. So
there's
iron,
2 choices. You've got iron and you've got sulfate. Now iron, what's charged iron on this?
That's plus 2 right there.
Because sulfate, of course, is minus 2.
Right.
So we're looking for something to go up. Now, sulfate, let's talk about it for a moment. It does have a redox reaction where it can turn to sulfite.
Sulfite, but that's going down.
But that is going down, so the sulfate is not going to do anything.
No, so
but
iron's going to go up.
But the iron can go up to ferric, which is Fe3 positive, and then we still need to put the sulfate over on this side of the equation.
Yep.
Now to balance this out, well, ladies and gentlemen, everything's balanced except the charge. So we don't have to play around too much with this. The charge on this side is 0, and this side would be plus 1. So I simply need 1 electron right there.
Yep.
Okay. Now to balance this out, of course, we need to multiply the bottom reaction by 5. And so everything cancels out. So it'll be 8H positive plus KMNO4 plus 5FeSO4 makes 5Fe3 positive. Mr. Sams is writing this down so when I go to the next screen, plus an Mn2 positive plus 4 waters plus potassium. Because I want to recopy this for the next screen. You probably will just continue on down on your paper, but I have a screen limitation. Actually, I think I know what I need to do, actually. So I'm going to go to another screen so I can answer this problem. I've got basically KMNO4 plus 5 FeSO4s. The key thing to that is actually just to get this and this coefficient, if I'm not mistaken, in this particular problem.
I believe so.
And so, yeah. So now we're going to do our BCA thing. What do I know? I have 50 milliliters. And what's the concentration of this, Mr. Sams?
0.1 molar.
0.10 molar. And the FeSO4
20
is
milliliters.
20 milliliters. And its molarity
It doesn't tell us. We need to find it because this is a titration problem.
So the question is, what's the concentration of the iron 2? And the iron 2 is in the FeSO4. So this is once it reaches the equivalence point.
Yeah, so we're titrating it. So
all right, well, I see a volume and I see a molarity.
Hey, look at that.
M times a V equals a moles. So we can take 0.1 times 50 would be 5. I had this theme going with the 5.
Yes, I'm seeing a theme.
5 millimoles of potassium permanganate over 1. And now I can use, you see I've got my mole-to-mole ratio, it's 5 to 1 or 1 to 5. So I can say 1 millimole of potassium permanganate is equal to 5 millimoles of FeSO4.
I bet you can do that one in your head, Mr.
I bet 5 times a 5 is a 25.
Yeah.
So we have 25 millimoles of the iron. Now, that's FeSO4. So some of you might be asking, I thought the question asks about the Fe2 positive charge. Well, remember, all sulfates are soluble, with the exception of barium, lead, calcium, and mercury. Well, this isn't either of those.
Nope.
It's iron.
It's
so
soluble.
This is actually also equivalent to the concentration of the iron 2 positive.
Right, the number of millimoles of the iron 2 positive.
The millimoles, thank
you.
The Fe2 positive would be equal to 25 millimoles. That's for the initial molarity?
Just the molarity.
Yeah, probably the initial molarity.
Yeah.
So you're not going to divide by 70. Some of you might be considering we should add them. But it's actually in just about this. So this would be over 20 milliliters.
Correct.
So 25 would be 1 point something.
Yep, 1.25.
1 1/4 molar. And that is the answer, folks. So these problems, they can ask so many different ways, so many different ways, and you've got to watch them and try and figure out how you're going to do them.
Yeah.
What do you think, Mr. Sam?
Yeah, I think that's about it, and we are done, and we're going to go out on a wonderful, beautiful note here of Mr. Bergman, not playing the cowbell, not the ukulele, not the kazoo, not the bucket, or the spoons, or the flute, but the violin. Now,
Something like that. I got to work on this.
now, Mr. Bergman learned to play the violin with his daughter. Everybody say "aw." Aw. All right, guys. Do well on your test. We'll see you in class. Bye-bye.